In this video, we're going to talk about the extreme values of a function. I'm going to talk about a few definitions before we start looking at the graph. So the definitions I want to start with are the absolute minimum and maximum on a graph and the local minimum and maximum on a graph. The absolute minimum, in colloquial terms, it's the lowest point on the graph's domain. So for that value, the height at that value is lower than any other height. The absolute maximum is the opposite, it's the highest point. The local minimum is the lowest point in a local neighborhood. And neighborhood is actually a mathematical term. It actually just means the open interval around a point. And the local max is the highest point in a local neighborhood. All of these are going to be really clear, and you can use intuitive sense when looking at a graph. We're also going to talk about when a function is increasing. A function is increasing if the slope is positive, meaning that the derivative is greater than 0. And the function is decreasing if the derivative is less than 0, meaning that it's sloping downwards. Let's look at these in relation to this graph. So this is a sketch of a graph, and on this graph we can see that there are some higher points and some lower points. On this graph there's only one. This is a local minimum because it's the lowest point in this neighborhood, meaning if I look to either side, it's lower than the points nearby. So this is a local min. And in this case, it's also the global min because it's the lowest point on the entire graph. There's nowhere else on the graph that's lower. So this is the local min and global is another word for absolute min. If I look over here on the graph, we see at this point, this is a point that is higher than the points nearby, so this is a local max. But it's not the absolute max because there are values, even though it's the highest one right here in this local neighborhood, there are values that get bigger and bigger and bigger over here on this side of the graph and over here on this side of the graph. And then we have one more point of interest, which is this one down here, and this is another local min. But it's not, again, it's not an absolute min because it's not the absolute lowest point on the graph. On this graph, it turns out that the function gets, these arrows indicate it gets bigger and bigger and bigger and bigger and bigger and bigger. So there's no absolute max on this graph, and that's okay. Depending upon the function, sometimes you have no absolute mins either. Let's now look at where the function is increasing and where the function is decreasing. When you're looking at the graph, it's really easy to be able to tell where the function is increasing or decreasing. The thing to keep in mind is to think about, as my x's increase, are my y values getting bigger or are my y values getting smaller? So sometimes it's tempting to look at this portion of the graph and say, aha, it's going up. So that way the function you might think that it's increasing here. And that's not correct because you want to look as my x values increase, my y values are decreasing. Another way to think of it is to say, aha, my slope of the tangent lines to the graph along here, they're all negative. So in this case, we see that our function is decreasing on the interval from -infinity until x equals 0. And there's a shift right here at x equals 0. Let's record that. So we just said that it's decreasing. I'll just continue. Yeah, we have enough space. So along this line, I'll write the intervals where it's decreasing. It's decreasing on the interval from -infinity until x equals 0. So this interval notation is the same thing as saying from my x values from -infinity to 0. And after that decreasing portion, then our slopes become positive. So on this interval, it's increasing. I think this is 1, 2, 3, 4, 5, 6, 7, etc. So on the interval from x equals 0 to 2, our function is increasing. So from 0 to 2, which can be written in interval notation, 0 is less than x is less than 2. We're increasing. That's what this is saying up here. And then we decrease again because as our x's increase, our y's are decreasing. And that's going on the interval from 2 until 5. So as 2 is less than x is less than 5. These are both our decreasing values. And then it's increasing again from 5 until positive infinity. So on the interval 5 to positive infinity, which you could write 5 is less than x is less than infinity is positive infinity. You could add a plus sign in front to make it more clear. So when you're looking at a graph, absolute maxes and mins and whether the function is increasing or decreasing is relatively straightforward. I want to introduce another idea, and this is the idea of finding max and min values when you're on a bounded interval. And this is a theorem that if we're looking at a closed bounded interval in terms of your x's, so we're limiting the domain of our x's, then every continuous function is going to have an absolute min and an absolute max. We saw in the last function, and here's that function again, that there was no absolute max globally on the entire domain, right? Because it just gets bigger and bigger and bigger. There's no one value that's bigger than all of the rest, because you could say infinity. That's not really a value, though. But if we restrict our domain to just looking at the interval from 1 to 8, so this is saying my x values are going from 1 is less than or equal to x is less than or equal to 8. What are the biggest and smallest of the y values on this interval? So let's take a look. When x equals 1, we're about right here. And I'm highlighting from x equals 1 all the way to where x equals 8, which is about right here. So we're going to restrict ourselves to just consider this interval. And what do we see on this interval? We see that our global min is still the same. This is the lowest part on the graph, and that's the point that it was before. And with the labels in this function, it looks like the point 5, -2 is the absolute min, as it was before. But now we see that we have these endpoints that we can evaluate. We see we still have this local max, but that's not the highest point on this interval. On this interval, the highest point is up here at the point 8, 5. So for an x value of 8, our function has a y value of 5. And that takes us to a final theorem that our goal today is to identify max and min values. And we see that max and min values are always going to be either the endpoints of these bounded intervals, or they're going to be what we call critical points. And critical points, you can see the local or max or min points. These critical points are places where the derivative is equal to 0 or where crazy things happen. So let's go to our definition. So a critical point, here we go, critical points. A critical point is a value x equals c where either the derivative at that point is equal to 0 or the derivative doesn't exist. So let's review what we saw before. Here we have a nice sloping function, and we see that our derivative is equal to 0 at this point. And so in this case, c is a critical point because our tangent line is horizontal, our derivative is equal to 0. And this is an example of a critical point that is a max. We could also have a critical point that's a min. This is another possibility that we saw before. Again, the derivative exists and the derivative is equal to 0. Here's a crazy one. So here's a crazy one where we can see on the graph that this is a min, right? It's the lowest point. It's a local min at least. We'll probably say that it's an absolute min as well because these arrows are saying that the function sort of goes up in that direction for the rest of the graph. But notice that the derivative doesn't exist at this point. The derivative is not equal to 0 because you can't really draw a tangent line at this point, right? It's a cusp. So this is an example of a min where my derivative does not exist, but it's still, in this case, an absolute min. Finally, the tricky part comes when, here's an example of a graph. It's a continuous graph where the derivative is equal to 0 right at this point C, but notice that it's not a max or a min, that this is something that we might call a dud. That the tangent line right at that point, I know it crosses the graph at those points, but right there, it's flat. The derivative is equal to 0 right here. So here we have f prime of c is equal to 0, and it's not a max or a min. And we can see graphically that that's an example. So if we're out hunting for max and min values, we're going to look at critical points, because critical points are a good place to start. We know that if it is a max or a min, it's going to be a critical point. But just because it's a critical point, that doesn't mean that it's necessarily going to be a max or a min. So that's our next question. How do we tell if a critical point is a max, a min, or neither? So if we're out hunting for maxes and mins, well, you can just look at the graph and you see whether the max or a min is, or whether the critical point is a max or a min. But sometimes we don't want to have to go through all of the effort of looking at a graph, and we want to be able to tell by algebraic means. So if I were thinking, like, here's a function. How can I tell whether this critical point right here is a local max or a local min? The first thing that we did is we saw that the derivative, so here's one thing that we know. We know that f prime at that point is equal to 0 or does not exist. So that's our first step in identifying the critical point, because we need to have the derivative equal to 0 or not existing to be a critical point. The next thing that I notice is that for this critical point, my derivative is positive as I go this way, and then my derivative is negative as I go this way. It's at the top of the hill, which means I climbed up the hill, it was flat at the top, and I climbed down the hill. So I can look at f prime at values less than c, maybe I'll call it r, as r approaches c from the negative side and as r approaches c from the positive side. And what's another way of saying that? Instead of having to look at the graph and looking at whether the derivative is positive on the left or negative on the right, this is where we can use our second derivative. Recall, so this is our second derivative test. Recall that the second derivative measures how much the slope is changing. And if I look at this graph on the left, I see that my slope is positive. My slope right at this point is 0, and then my slope is negative as I go down the hill. What does that mean for our second derivative? It means what is the rate of change of my derivative? And my derivative is getting smaller and smaller and 0, and then more and more and more negative. In other words, this is a graph where my second derivative at this point C is less than 0. Another way to picture this is that the graph is being pulled downwards. So anytime that my graph is being pulled downwards, it means that my slopes are getting more and more and more negative, or they're getting smaller and smaller and then more negative. Oops. And it means that C is a max. I would rather if you didn't memorize this, but you can sort of intuitively look at the graph and figure out what's going on. Similarly, here's my other example where the derivative is negative, it's negative, it's negative, and it's getting bigger and bigger. Or in other words, my second derivative at this point C is greater than 0, that my graph is being pulled upwards. and C is a minimum. Another way to think about it is whether or not this cup holds water. If my cup holds water, it means that my second derivative is positive, and my value has to be a local min. Why is all of this important? Let's say we don't have a graph and we have to evaluate algebraically whether or not our critical points are maxes, mins, or neither. Oh, I left out one case, right? Our second derivative is equal to 0. Our second derivative is less than 0, is greater than 0, or if it's exactly equal to 0, that's going to give you the dud case. Because looking back at this dud case, if my second derivative is equal to 0, that's double prime of C is equal to 0, it's not getting pulled up or pulled down. Like it's sort of pulled down on this side and it's pulled up on this side, but right at this place, it's not a cup in either direction, and my second derivative is going to be equal to 0. So this is my dud. It's not a max or min.